Hi, everybody. It's Professor Mitchell. We're continuing Chapter 10 on correlation and regression. And actually, the only other thing we're going to do from this chapter is Section 10.2 on regression. So the key concept in this section is to present methods for finding the equation of the straight line that best fits the points in a scatter plot of paired sample data. That best fitting straight line is called the regression line, and its equation is called the regression equation. I'm going to stop there because I'm actually going to, we will talk about marginal change, but I'm not going to talk about influential points and residual plots. So what is a regression line? Given a collection of paired sample data, the regression line or line of best fit or least squares line is the straight line that best fits the scatter plot of the data. The regression equation is written y hat equals b sub 0 plus b sub 1 x. So this is kind of like the statistics version of y equals mx plus b. That algebraically describes the regression line. The regression equation expresses a relationship between x, called the explanatory variable or predictor variable, or I usually call it the independent variable, and y hat, called the response variable or dependent variable. So the objective of this section is to find the equation of a regression line. Notice there are some differences in notation depending on whether you're working with a sample or a population. So keeping with tradition, sample statistics are usually written with regular letters. Population parameters are usually written with Greek letters. So as I mentioned, we have B0, B1, and then y hat equals B0 plus B1x. If we're working with a population, the y-intercept becomes beta sub 0, and the slope becomes beta sub 1. The requirements for finding the equation of a regression line. First, the sample of paired XY data is a random sample of quantitative data. Number two, visual examination of the scatter plot shows that the points approximate a straight line pattern. And third, outliers can have a strong effect on the regression equation, so we want to remove any outliers if they are known to be errors. Consider the effects of any outliers that are not known errors. This slide here, we're getting into the weeds a little bit. I'm not going to read this. If you're really interested, feel free to pause the video and read it on your own, but I'm going to go on. Okay, so I made some changes to this. Sort of like in the last section, they gave you two different equations for the correlation coefficient, and I said that I was only going to use one of them. They did something similar in this section, and I decided I wasn't even going to bother with one of the equations that they gave me. Actually, one equation for B1 I decided not to bother with, and one equation for B0 I decided not to bother with. So you can use technology to find B1 and B0. I'm going to show you a slide that kind of shows that a little bit. I'm not really going to use it much myself, except for using Excel to help me with some of these calculations inside the formula. So you'll see that a little bit. We'll use this equation to find B1, which is the slope. And then once you've found the slope, it's really easy to find the y-intercept. The y-intercept is just y bar, which is the mean of the y data, minus B1 times x bar, which is the mean of the x data. The rounding rule is round B1 and B0 to 3 significant digits. It's difficult to provide a simple universal rule for rounding values of B1 and B0, but this rule will work for most situations. And actually later on, I just realized that I saw them, oh no, they did use 3 significant digits. Never mind. All right, so in this example, they're first going to use technology to find the equation of the regression line in which the explanatory variable or X variable is chocolate consumption. This is the same example from the last section. And the response variable is the corresponding Nobel laureate rate. The table of data is actually on the next two slides. So here's part of it, and here's the rest of it. Okay, for checking the requirements, the data assumed to be a simple random sample. The figure is a scatter plot showing a pattern of points. This pattern is very roughly a straight line pattern. You can kind of imagine a straight line passing through those points. And there are no outliers, so the requirements are satisfied. The use of technology is recommended for finding the equation of a regression line. On the next slide are the results from different technologies. Minitab and XLStat provide the actual equation. The other technologies list the values of the y-intercept and the slope. All of these technologies show that the regression equation can be expressed as y hat equals negative 3.37 plus 2.49x, where y hat is the predicted Nobel laureate rate and x is the amount of chocolate consumption. So here are those technologies. Here's StatDisk, XLStat, which is a plugin for Excel that I actually tried to install myself at the beginning of the semester and gave up after a while. Minitab, SPSS, for those of you who have a TI-83 or 84 graphing calculator, it looks like this. I've never even heard of JMP. And then StatCrunch, which you've seen sometimes in your online homework. We should know that the regression equation is an estimate of the true regression equation for the population of paired data. This estimate is based on one particular set of sample data, but another sample drawn from the same population would probably lead to a slightly different equation. All right, so now we're going to use the formulas for B1 and B0 to find the equation of the regression line in which the explanatory variable or X variable is chocolate consumption and the response variable or Y variable is the corresponding number of Nobel laureates. And we've already checked the requirements. So we're going to begin by finding the slope, B1, and as I mentioned, I'm going to use Excel just to speed up the process of finding the sums of the necessary columns. So let's back out of PowerPoint here for a minute. I'm going to switch over to Excel. So you can see that I've already loaded up all of the sample data. So the four things that go into that big, scary formula that we were looking at a few minutes ago, we need the totals of the X column, the Y column, the X squared column, and the XY column. So I think I'll start by making my X squared column, and that's really easy in Excel. You just go to the first cell, put an equal sign, and then select the first X cell, C-E-L-L, all right? So it's referencing cell B2, and now I'm going to tell Excel that I want to square that cell. Okay, and I remember recently I talked to you about using cell references in formulas as opposed to just typing 4.5 squared in this cell. It's a lot better to use cell references because now what I can do is copy this cell and select all of these cells. And as soon as I hit paste, Excel is going to assume that what I want to do in each and every cell is square the value that is 2 cells to the left of the one I'm in. And presto, there it is. Okay. So now I'm going to do something similar with XY. I'm going to put an equal sign. I'm going to reference this cell, and then I'm going to say times, and then I'm going to reference this cell. So it's telling Excel to multiply the two cells that are 3 cells to the left and 2 cells to the left. So that's what it's going to do in that cell. And then again, when I copy and paste, it's going to use the appropriate cells for every single one of these. So I just love Excel for doing this kind of stuff. And now, as I mentioned, I need the totals of all of these columns. So I am at the bottom of the X column, where I'm going to type equals sum, and then I'm going to tell it to sum all of these values. And you see what it put right here. That's Excel notation for find the sum of cells B2 through B24. So I'm going to close off this parenthesis. And I find that the sum of the x's is 133.5. And again, because I used cell references, when I copy and paste that cell into here, it knows that what I want to do is sum all of those columns with the correct values. Okay. So it's what I sometimes call high-tech, low-tech. I'm not having the computer calculate the, just go right to the equation of the regression line, but I'm using the computer to help me with some of the more, tedious calculations. So now going back to PowerPoint. All right, I did this beforehand and I copied the totals here. So this is the sum of the x's. This is the sum of the y's. This is the sum of the x squareds. And this is the sum of the xy's. So here's the big scary formula again. N is 23, which is the number of pairs of sample data. The sum of the xy's is 2072.23. The sum of the x's is 133.5. Sum of the y's is 255.4. The sum of the x squareds is 1011.45. And then again, notice the difference between this and this. This is saying to square the x's first and then add them up. This is saying to add the x's first and then square the total. So that's why you see two different numbers here. And when you crunch those numbers, you get 2.49313, blah, blah, blah. So that's, we saw that 2.49 a little while ago, right? That was the answer that they said they got from technology. So now it's really easy to find B0, which is the y-intercept. You just do y bar minus B1 times x bar. One thing I did forget to do in Excel was I forgot to use Excel to find y bar and x bar. I've shown you how to do that before with the average formula. So we'll take their word for it that y bar is 11.1043 and x bar is 5.8043. And for our y-intercept, we get negative 3.366675. Okay. All right. And they said to round those values to 3 significant digits. So that would be 2.49 and negative 3.37. So the regression equation is y hat equals negative 3.37 plus 2.49x, where y hat is the predicted Nobel laureate rate and x is the amount of chocolate consumption. So the next thing we're going to do is graph the regression equation on the scatter plot of chocolate Nobel data and examine the graph to subjectively determine how well the regression line fits the data. So they have just gone ahead and used technology for that. Shown here is the mini tab display of the scatter plot with the graph of the regression line included. So I'll just mention briefly for now, and maybe if need be, I'll make a follow-up video on this later. In order to graph an equation like this, the first thing you can do is plot the y-intercept, which would be at 0, negative 3.37. Okay, as I was talking, I decided it would probably be a good idea to show you how to graph these linear equations, just in case you forgot. So remember, the equation that we just found is y hat equals negative 3.37 plus 2.49x. So the first thing I'm going to do is plot my y-intercept. So the y-intercept at negative 3.37 means 0, negative 3.37. So I've marked these off by ones. I'm kind of proud of myself. I just figured out how to download this graph paper grid and add it as an image onto my, little whiteboard here. So I'm discovering all sorts of cool toys as we're all forced into this, remote instruction situation. Okay, so I see negative 3 here. I wish there was a good way to point at this. Negative 3.37, oops, is probably right about there. I don't know how to keep that from popping up all the time. All right, now the slope of 2.49 means that every time, means rise over runs. So every time we run 1 unit, we rise 2.49. I'm just going to call that 2.5. Okay. So if I run 1, which would be right about here, I'm going to rise, we'll just call it 2.5. So this would be 1, 2, it would put me right about here. All right, and I'll figure out how to keep that from doing that in a little while. Maybe we'll do that one more time. Run 1, and then rise 2.5. So I left off at about negative 0.8. If I rise 2.5, that's going to put me at about 1.7, right about there. All right, so my the equation of my line will look something like this. All right, just in case, I have a feeling you probably will have to graph these lines in your homework. So hopefully that helps. All right, going back to the PowerPoint. All right. So this is the graph they came up with. It looks a lot different from the one that I did just because they're using a different scale for the X's and the Y's. All right. So we can see that the regression line fits the points well, but some of the points are not very close to the line. All right, in terms of making predictions using regression equations, they're often useful for predicting the value of one variable given some specific value of the other variable. But when making predictions, we should consider the following. Number 1, if the regression equation does not appear to be useful for making predictions, then we shouldn't use it. For bad models, the best predicted value of a variable is simply its sample mean. All right, but if you have a good model, use the regression equation for predictions only if the graph of the regression line on the scatter plot confirms that the regression line fits the points reasonably well. Number 3, in terms of correlation, use the regression equation for predictions only if the linear correlation coefficient R indicates that there is a linear correlation between the two variables. So we talked about that in the last section, and determining whether R does or does not indicate that there is a linear relationship, that's actually a hypothesis test. all right? There is no specific value of R, like if R is greater than 0.6, then it's a good model, because that depends on the sample size. And finally, use the regression line for predictions only if the data do not go much beyond the scope of the available sample data. So what they mean by that, if we can go back to, oh, we can get it right from here. So notice that the numbers for chocolate consumption all lie between 0 and 12, okay? So that's what they mean by scope. We should only use this equation to make predictions for values of X that are pretty close to the interval from 0 to 12. Like if we wanted to predict it for X equals 13, that would probably be okay. I would not use it for X equals 20, 25, 50. All right, that's way outside the range of X's from the sample. The figure on the next slide summarizes a strategy for predicting values of a variable Y when given some value of X. And I think this says all the same stuff that we were just talking about. So if you want to take a couple of, a minute or two to look at this, I'll let you pause the video because I don't think it says anything new that we didn't talk about on the last couple of slides. All right, as an example of making predictions, first we're going to use the chocolate Nobel data to predict the Nobel rate per country with chocolate consumption of 10 kilograms per capita. And then in letter B, predict the IQ score of an adult who is exactly 175 centimeters tall. Sounds like it might be a trick question. All right, for letter A, we did decide that the regression equation was a good model. There is a linear correlation between chocolate consumption and Nobel laureate rate. We determined that in the last section. So because this equation is a good model, we'll substitute X equals 10 into the regression equation. So you see how that would work, right? You would just replace X with 10. So 2.49 times 10 is 24.9. 24.9 minus 3.37 gives you approximately 21.5 Nobel laureates per 10 million people. Okay, so if we had a regression equation for height and IQ score of adults, I can pretty much guarantee you that we would decide it's a bad model because there is no correlation that I'm aware of between height and IQ score. All right, so knowing that there is no correlation between height and IQ score, we know that a regression equation is not a good model. So the best predicted value of IQ score would just be the mean IQ score, which is 100. Right? And that is not necessarily something I would expect you to just know off the top of your head. They've done many examples with IQ score, and I think the mean was almost always 100. But all right, so the interpretation in part A, the paired data result in a good regression model. So the predicted Nobel rate is found by substituting the value of X equals 10 into the regression equation. In part B, there is no correlation between height and IQ. So the best predicted IQ score is the mean Y bar equals 100. So the moral of the story is use the regression equation for predictions only if it is a good model. If the regression equation is not a good model, use Y bar. Okay, marginal change. This is where they talk about the meaning of the slope of the regression equation. In working with two variables related by a regression equation, the marginal change in a variable is the amount that it changes when the other variable changes by exactly 1 unit. The slope B1 in the regression equation represents the marginal change in Y that occurs when X changes by 1 unit. And you actually saw me using that when I was drawing the graph of the regression equation. At one point, I reminded you about rise over run, and I said you could interpret that 2.49 as 2.49 over 1, all right? So the 1 means every time I increase x by 1, y increases by 2.49, all right, which is essentially what this says here. Let's consider the 23 pairs of chocolate Nobel data. Those 23 pairs of data result in this regression equation. The slope of 2.49 tells us that if we increase x, chocolate consumption, by 1 kilogram per capita, the predicted Nobel laureate rate will increase by 2.49 per 10 million people. That is, for every additional 1 kilogram per capita increase in chocolate consumption, we expect the Nobel laureate rate to increase by 2.49 per 10 million. All right, and finally, just a reminder that in a scatter plot, an outlier is a point lying far away from the other data points. I think they brought this up to get ready for some other stuff that they were going to talk about later, and I decided it wasn't important to cover any of that, so I believe we are done with section 10.2. See you next time.